Okay, in this presentation we want to look at a new concept, the concept of acceleration, which is listed here as being a rate of a rate, and I'm going to talk about what that means. But it's worth noting that the first real systematic view of motion was carried out by a guy named Aristotle, and you've probably heard of Aristotle. He's very famous. He is famous as a Greek philosopher from ancient Greece, and he's also famous as the father of biology. So he's considered the progenitor of one of the major branches of science. He also wrote a lot about physics, and specifically he wrote two books, one of them called Physics, and that's actually where the name physics comes from. It's the Greek word for nature. And so Aristotle wrote a book called Physics, and he wrote another book called Metaphysics, which is basically means beyond nature. You might think of that as being supernatural, but not like ghosts and vampires and stuff. It's supernatural in a very different way. His book on metaphysics is really weird, but his book on physics is interesting because he really did analyze a lot of things about motion, but unfortunately, most of the things that he came up with, most of his ideas were incorrect. Now, they weren't crazy, they made sense, but they just happened to be wrong. Now, a lot of these views that Aristotle had that were incorrect, they were unfortunately accepted by the Catholic Church. They were incorporated into church dogma, and this was back in the days when the Catholic Church was the only Christian church around, really, and it had really absolute political power. And so you would not go against the Catholic Church in those days because bad things would happen to people who did. And when the Catholic Church said Aristotle's our guy and his views are right, people didn't question that. And so Aristotle's views were accepted for a very, very long time until they were finally upended by the work of a guy named Galileo Galilei. Now, you might have heard of Galileo. He's pretty famous now. He was the person who decided to actually employ the techniques of the scientific method and test the views put forth by Aristotle. And when he made those tests, he found that those views were simply wrong. Now, in particular, Galileo was very interested in studying the concept of motion. And so he did a lot of experiments with things that were moving. And in particular, he was interested in the motion of falling bodies. So if you drop something, how does it move? And, if you drop something from a meter or so high, it hits the ground in less than a second. It's very, very fast, and it's hard to analyze that motion because it happens so quickly. So he did something really clever. He built these long inclined planes, basically these ramps, that he had cut polished grooves down the middle as sort of a channel for balls to roll down. So he was able to roll balls down these long ramps. And so instead of taking, a half a second to reach the ground, they would take maybe 5, 6, 7, 8 seconds, and he could measure how they moved with time. Now, another advantage that Galileo had over Aristotle was the fact that Aristotle didn't have a clock. It's really hard to do experimental physics if you don't have an accurate way of keeping time. And Galileo had a clock. It was called a water clock, and it was basically a bag filled with water that had a valve attached to it that would let water drip out at a steady rate. And so drip, drip, drip. Each drip was like the tick of a clock, and he could see how far his balls moved per drip, and he could measure out and analyze their motion. Now, through his experiments, Galileo managed to come up with a new idea, and it's an idea that's obvious to us today, but until someone had figured it out, it wasn't obvious to people. And so let's recap what we know so far. So we've seen how we can describe velocity, and velocity is the rate at which position is changing. So it's the displacement over time, or the change in position over time. It's the rate at which position is changing. And through his measurements, Galileo found that for falling bodies, the velocity of the body was constantly changing too. And this was a new idea that he came up with, the idea of acceleration being the change in velocity with respect to time. Now, here was the thing that was really brilliant about Galileo's discovery. He found that not only was the velocity changing, It was changing in a regular pattern that could be described by a mathematical relationship. And so math would be able to be used to analyze this kind of motion. So just as the position can change with time, so can the velocity. Things can speed up, they can slow down. The velocity can change. The rate at which velocity changes is called the acceleration. And so we can have a definition here for acceleration. The average acceleration is simply the change in velocity over the change in time. And we can note velocity is a vector. That means that acceleration is also a vector. Okay, now we can look at the units of acceleration. And we know that acceleration is delta v over delta t, the change in velocity over the change in time. Now velocity has units like meters per second, some kind of distance over time. It could be miles per hour, whatever, but usually we're going to be looking with meters per second. And then the time, so we've got delta v over delta t, meters per second over seconds. And of course, mathematically, this second is technically in the same denominator that that one is, so I can group these seconds together, and when you multiply seconds together, you get seconds squared. And so the normal way that you would write and say the unit for acceleration would be meters per second squared. But this formulation here actually gives you maybe a little bit more idea about what it means. So let's say that we have a ball that we're holding up, and so it's at rest. It is not moving at all, and then I let go so that it falls. It turns out that everything that falls near the surface of the earth falls with a rate of about 9.8 meters per second squared, or 9.8 meters per second every second. Just to make our life a little easier, let's guesstimate that. Let's call it 10. We'll round up to 10. So we'll say that things fall 10 meters per second, that's their acceleration. So what does that mean? Well, this guy's dropped from rest, so it's got zero velocity when it starts. And after 1 second, it's going to have 10 meters per second. That's going to be its velocity. After 2 seconds, it's going to be going 20 meters per second. At 3 seconds, it's going to be going 30 meters per second. So every second it gains 10 meters per second in velocity. That's the change. There's a change of 10 meters per second velocity every second. So that's what we mean when we say 10 meters per second, or more commonly, 10 meters per second squared. Again, it's just the rate, how much velocity change you're getting every second. Now we've looked at some plots of position versus time. We can also plot velocity versus time. So let's consider motion among one dimension. So we're going to consider motion that's constrained to be moving along the x-axis. And we're just going to look at this graph. And what does this graph tell you? What's going on? We can see that the velocity starts with zero velocity, then it increases, and then it decreases back to zero, and then eventually it becomes negative. And so what does it mean that the velocity is negative? That means that at this point it's actually changed direction. And so if you were looking at this graph, a lot of people tend to view them like position versus time graphs. They mix them up in their head. If this were a position versus time graph, if I had, x versus t, we've already talked about how, if I've got x versus t, at the top here, that's where the velocity is zero. And so a lot of people will make a mistake and they'll think, oh, up here the velocity is zero. But really, where's the velocity zero? The velocity is zero there, and the velocity is zero there. And so what's happening here is there's a change between the velocity increasing and it decreasing. And so what's actually zero there, we'll see, is the acceleration is zero there momentarily. But the main point that we want to make is that you don't want to mix up velocity versus time graphs with position versus time graphs, because they indicate very different things. So when you see these graphs, keep in mind when you're talking about the velocity and when you're talking about the position. Now, if I look at 2 points, say a point right there and a point right there, 2 points on a velocity versus time graph, they will be some time interval delta t apart, and there'll be some difference in velocity, delta v. And if I draw the rise over the run, delta v over delta t, that's going to be the slope of that line. And so that tells us we know that the slope of that line, delta v over delta t, that is just the average acceleration. So I can note that the acceleration is going to be the slope of a velocity versus time graph. And so that's a very important idea. Okay, so here we're going to look at instantaneous acceleration. And we have a formula here. The instantaneous acceleration is equal to the limit as delta t goes to 0 of delta v over delta t. Now, of course, delta v over delta t is the average velocity, but we're taking the limit as delta t goes to 0. So instead of taking, the average velocity from the starting point to where it ends, we're looking at the velocity at a particular point in time. And so we want to take the interval, the velocity, we want to take the average velocity over a small time interval around that point, and then let that time interval get smaller and smaller and smaller and smaller until it zooms in on that point. And here's the key thing. This process of letting that limit go to 0, taking that time interval and letting it shrink as close to 0 as you can get with not actually getting there, because you're not allowed to divide by 0 in math, this process is called taking the derivative. And if you ever take calculus, you'll learn all about how to calculate derivatives, and this is how we would actually write out the derivative, dv over dt. But your guys in general physics aren't going to have to calculate the derivatives because you don't have to do calculus. But the thing is that I want you to recognize it, that we can actually in principle calculate a value for the acceleration at every point on this curve. And that acceleration is changing. Now, one thing that you can take from calculus, and you can just take my word from it, you can actually prove it with calculus, the value dv over dt, that's equal to the slope of the line that is tangent to the curve. Now, we talked about that in terms of the slope of a position versus time graph is the velocity. Well, here we can see the slope of a velocity versus time graph is the acceleration. So when you look at the acceleration, you're going to be looking at the slope of the velocity curve. So that's kind of a useful thing to know. And so we can look at this blue line. This blue line represents the velocity as a function of time. And so we can see a few things about this motion. We can see that it starts at 0, so it's starting from rest, and then the velocity is increasing. Now, keep in mind, this is not the position that we're talking about. This curve is just describing the velocity. We don't want to mix up velocity graphs with position graphs, and that's a big mistake that a lot of people make. They see a curve like this, and in their head, it looks to them like a position curve, and so they think that they can apply all the things they know about position curves. Doesn't work. We have to analyze a velocity curve in terms of the velocity. So let's see what's going on here. So it starts from 0. We've got a positive velocity. How do I know it's positive? Because it's above the 0. So all these values are positive values of velocity. That means what? It's going in the positive direction. And here we can see that there's a positive slope. So the slope is positive. Now, over here, we can see it's got a negative slope. And so the negative slope tells us that it's going to be slowing down. In other words, here it's speeding up, here it's slowing down. It's not as fast as, it's slower here than it was up there. The slope has changed and become negative. Now here's an interesting thing. Right here is when the velocity is 0. And so at that point, the object actually stops. And then the value of velocity becomes negative. So it could stop here and then keep going in the same direction, in which case it would go up there. But the fact that it crosses into negative velocity territory means that there's a minus sign in front of the vector and it's changed direction. So here it's getting faster and faster and faster. It gets the maximum velocity. It's slowing down, It gets to 0. It stops for just a moment and then it reverses direction. Now the slope is still negative here, but it's speeding up. I'm getting bigger and bigger values in the negative direction, so it's going faster and faster in the negative direction. So let's look at another velocity versus time graph. We can look at some of the qualitative features. So first of all, the first thing that we can notice is that it starts, here's t equals to 0. It has a positive initial velocity. So it doesn't start with 0 velocity. When I start my stopwatch and I start taking data, this thing's already going. But we can see that its velocity is getting smaller, it's decreasing. And here, at this point, it is 0. So at this point, the thing momentarily stops, and then the velocity changes direction, and it's going in the negative direction. And then it comes a point where basically the velocity is not changing. The acceleration is 0 from here to here, so I've got a constant, steady, negative velocity, and then it's going in the other direction back to 0 where it stops. And so that becomes the way of tracking this and understanding how to interpret these velocity versus time graphs. You look at the slope and you look at the values, whether they're positive or negative, and that tells you the information that you get from that graph.